technical problems.
There was something about quantum and elliptic curve crypto being the same. Maybe it's hardened or spartan against even Q quantum for a while.
No, I don't think so.
It's not.
I think, like all other public key systems, quantum computers will greatly hurt it, and you'll have to have key length like at least 3 times as long.
What you guys going? Right?
That's what the NSA says, and I know the serious quantum computer researchers say it's going to be much worse than that. They say that if we get the quantum computers working, we're going to have to abandon all current public key systems.
Wow,
But the question is, how good are the quantum computers going to be? And that's what we don't know yet. But in principle, the quantum computers could change the order of complexity from like exponential to square or something, which ruins the whole thing. They said even 1 million bits in the public key wouldn't be enough anymore.
If you go from exponential to square, is an exponent.
Well, that's a polynomial. Right now, it's like 2 to the n.
Yeah.
So it gets huge really fast. It's going to go down to like n squared. So it's going to be just many, many orders of magnitude easier to calculate. And so, yes, programming a quantum computer will be completely different.
Three-dimensional, right?
Yeah. Yeah, I don't even know how you'd write code. I think you pretty much have to design a structure which has minimum energy as a solution. You have to start with the gas and cool it and let it condense into the solution.
So you have to basically play with quantum physics every time you code?
Well, they'd probably invent some general language or some kind of general hardware that can have some parameters connecting to qubits that you can adjust. But yeah, it'll be completely alien at first.
IBM's working on something, right? I saw something that read just recently, a couple of days ago.
Let's see, today, no project due or something due today that didn't exist yet, so people were upset about that. Right. So I probably wrote that project, but it's not due for a couple of weeks. 11/20, 13 and 14 due. Okay. I saw somebody had a new quantum computer out. IBM had 50 bits, I think. Yeah, 50 qubits. And so people are saying it could be awesome, but the problem is it depends on how noisy it is. That's the problem. You can only do these complicated calculations if the qubits can be coupled and they are exactly perfect to high precision. And whatever they're building are only approximate. So Tuesday, Thursday, November 14 and 16. These guests. 388, 6 p.m. All right. I've heard good things about this guy, so he's coming.
He's tomorrow, right?
Tomorrow and Thursday.
Okay.
So, yeah. All right. And I remember there was actually a lot of exciting news. There we go.
Intel got in trouble for something.
Who did?
Intel. Apparently something to do with a backdoor in some of their chips.
Well, yeah, I heard about Intel having a baseband issue where, well, not Intel. Well, I'm not sure about that one. I think it is Intel. Yeah, Intel has like a management interface, which people didn't know about, and now they're getting very upset. Quite so. This one I was just reading about, which is interesting. That's probably the best explanation of it. I think these are probably the ones I think are most interesting. So this one here, Bitcoin Gold is out, the latest Bitcoin fork. And the thing about this is they fixed the centralization problem. They switched the proof, the mining process from the current system, which is SHA-256 hashes. So it depends entirely on CPU. So no one can do it except people have the fastest ASIC, to a new algorithm called Equihash, which is what Zhash uses. And this, I got the research paper linked in the news. This is very interesting. Here's the idea. You take the block of data and you run it through a pseudo-random number to create a whole series of semi-random numbers from the block. And then you solve the generalized birthday problem. Remember, the birthday problem is where you have a room full of people and they call out their birthday and see if two of them have the same birthday.
It's 43 or something.
At 23. 23 people before you have 50% chance that two of them have the same birthday.
43 is like 98%.
Probably, yeah. And this one here, you take a lot of these random numbers and you make it so you XOR them all together, you'll get 0. So this means if you line them all up and count the ones, the number of ones in every column has to be even, sort of like Sudoku. So that is another very difficult calculation, very rare to occur. But the point of this one is, as you can imagine, it's enormously better to have a lot of memory. Because if you can hold a whole lot of them in memory, then it's very easy to do this calculation over and over and over, hunting for a group of 2 to the 1,000 out of 2 to the out of a larger set, finding a subset of them that will have this property. So the more you can store in memory, it's better. And they say it's enormously better. Where if you have 700 megs, you can do it in 15 seconds. But if you have 250 megs, it takes 1,000 times as long. So it is designed not to run on CPU power, but on memory, because there is no, apparently they think memory will be more evenly distributed around the world. Apparently there's no particular reason why the Chinese will be able to afford a lot more memory than everybody else.
It won't be distributed memory like distributed computing. It will be like everybody will have access to their own.
Well, I would think so. That's another issue, is exactly what would happen with a cluster. And can people cooperate and make like pools that all work together? And I don't know the answer to all that, but they had thought of these things, I think, in plan. That's why Zcash uses it, and now the new version of Ethereum uses it. And the idea is that it will not be dominated by one country anymore. It will be democratic. Everybody will have an equal chance. Like $1 million in US to buy a lot of RAM would be as good as $1 million in China buying a lot of RAM. Whereas right now, it's not that way at all.
With China's like major manufacturing, but base in computer parts, wouldn't this just change it over again?
It's possible, but I think the idea is, and I should repeat for the people that remotely, if China makes all the chips, wouldn't that give them an advantage? And I don't think so, because the people who make the chips are not mining. They just cheerfully sell the chips to anybody. So, however, if they could get the chips like vastly cheaper in China, then we can get them here, then that might be an advantage, I guess. But anyway, apparently it's currently happening for Zcash and now for this version of Bitcoin, which is still a fringe currency, but it's interesting because people talked about this. Certainly, this is one of the many things that make me not want to invest in Bitcoin, is the fact that right now it's completely dominated by China. So I don't know what the real difference is between just buying Chinese currency and buying Bitcoin. Is you're totally betting on the government of China. And they can make it wave up and down with every word they say. And so a lot of people don't like that. So this would probably make Bitcoin back to what the original developer wanted it to be, which is a currency not owned by any one country. Now, you could certainly argue whether that's a really good idea, but anyway, that was what he wanted, and this would probably do that. So the guy that ran Mt. Gox, which was the largest Bitcoin exchange, and then all the money was stolen in a few days, or he stole it or somebody stole it. Nobody really knows. And he was going to have a prison term and everything else. Well, now he's made a deal that he's going to pay out people's claims at the price of Bitcoin then, not the price of Bitcoin now, which makes an enormous difference. So he's going to walk away with a giant pile of cash because the remaining Bitcoins have inflated so much that he can pay everyone off and go home with a lot of cash too. So
it's like 90 cents on the dollar, isn't it?
Well, they say it's different between 440 and 6,500. So like 5 cents on the dollar. Yeah. So that's, of course, that's an interesting issue. Anyway, we'll see what comes.
Like in the Japanese bankruptcy law, that says you market.
Yes.
So that it,
yeah.
Lost, not the current market.
Yep. And this is the problem with highly volatile things that change value so fast.
Yeah.
A delay in paying you out makes it.
Personally or a company?
Well, I think it's complicated. To some extent, he's criminally liable. To some extent, it's a company he owns. That's why I think the difference is also complicated in Japanese law and American law. But this apparently is under Japanese law.
So how does he pay for like someone in Europe and then America if it's Bitcoin international?
I think he wants to give him back the current value. I think he wants to pay. I think he has some Bitcoins left. They inflated so much now he has enough money to pay everybody off, as long as he only pays them 5% of the dollar. But I don't know all the details. But so anyway, I thought it was an interesting one, but I don't know all the details of it. This one here I thought is very interesting. Bruce Schneier, who is a real security expert, testified before, I think, Congress, or the Consumer Protection Commission or something about the Equifax hacks, and his conclusions were quite interesting. It was a serious breach, put millions of Americans at risk. I can buy that. Equifax was solely at fault. It was not a brilliant attack. It was a simple program. They didn't patch their stuff, and they got owned by a patched vulnerability. And his point, I'm glad he's saying it, there are thousands of other data brokers with similarly intimate information, similarly at risk, and they deliberately hide their actions and make it difficult for consumers to control their data. There's no regulation over them that matters. They're all doing this without our consent, without our help. We didn't join Equifax or voluntarily give them our data or anything. They collected the data and then lost it, fouling up all our lives. And the market can't fix it because we are not the customers of data brokers, which is, I think, a very good point, especially for a Republican administration that believes in market fixes. And so we need regulation. I don't think there's any chance of it happening, but he's a good voice in the right area. So resist complaints from industry that this is too hard. And this has foreign trade implications, which I imagine it does. And like I say, Europe may push us into this. It is increasingly the case now that the United States is a backward country being pushed forward by other nations on things like climate change and high tech. China now has beat us in the number of supercomputers. They've been beating us for 5 years. We're now at the lowest we've ever been in 20 years in the number of supercomputers we have in the top 500. We're falling way behind, and we're also far behind on civil rights and privacy, and Europe is pushing us forward there. So, we appear to have had our time leading the world, and now we're being dragged forward by the world unwillingly.
Before China, wasn't it Japan with a supercomputer?
Well, I think back then the U.S. was a lot bigger. Yeah, but Japan had some, yeah.
It's also it's tougher to have more advanced, further advanced in the semiconductors area.
Yes, that's an issue, yeah.
So a lot of people can catch up, so you cannot do it.
Yeah, well, I think we could do a lot more, but we're not doing it. We've changed to sort of.
Person can only invent so fast, right? So,
well, sure, but rather than putting money in development and science, we've been hiding and putting money in like protecting ourselves and expelling foreigners and stuff. The scientific committees are now run by Donald Trump's golf caddy and stuff.
he's not doing anything now.
Oh, he is. But anyway, and the EPA is no longer interested in the environment. And this, he's doing what he can to prevent scientific progress, and he's had some ability to do it. But anyway, yeah.
Yeah, this article they said some Australians, French, and Singapore people.
Yeah.
They said they were saying that a quantum computer will run a short algorithm against cryptocurrency's protective curve signature quicker than the 10 minutes Bitcoin needs to record the transaction in blockchain. Yes, that's right. There was an article saying Bitcoin is going to be big trouble. The current Bitcoin, if quantum computers work within about 10 years, they will be able to completely mess up the Bitcoin blockchain. So they're going to have to make some adaptation. Anyway, so we're up to elliptic curves. All right, so that's an example of elliptic curve. Elliptic curves are not ellipses. They are something that is used in the math of calculating the circumference of an ellipse. They're peripherally related to ellipses. So here's the game. This has been around since the 80s, and you get the same level of security at RSA with shorter keys and much faster calculation. They use less network bandwidth because everything is smaller, and they use less CPU because the calculation is using smaller keys. So we're going to talk about the pros and cons of elliptic curve, RSA, and discrete logarithm schemes. What an elliptic curve is, how to build a discrete logarithm, and the protocols and security of these. So with elliptic curves, now a circle has this equation, x squared plus y squared equals r squared. That gives you a circle. If you multiply x squared and y squared by constants, you stretch the circle one way or the other, and now you have an ellipse. But an elliptic curve is y squared equals x cubed plus ax plus b. That's what creates this funny looking thing. And that is the thing that has the mathematical properties we want. So if you run it on the real numbers, you get this curve. But we are not going to use that. We don't want real numbers. We want integers in a ring. That's always what you want for cryptography. You want a ring of size n that's going to loop around. And you want integer input to make integer output. So you can put in some bytes and get out some bytes. So you use the same mathematics, but you implement it on integers. So you have a pair, x, y, which are integers, and you have a mod of p, and then you use the same formula, x cubed plus a times x plus b mod p.
And remember, to make a group out of this, you have to have an identity element. And the operation, which we're going to define, the identity element is the point at infinity. Infinitely large values are the ones that have the desirable property. So that's the identity point here, theta. So adding infinity to something leaves it alone in this crazy system. And the reason why it works is because this operation that we're writing down as multiplication is a screwy operation we're going to define. Remember, from a group theory point of view, any operation that just takes an integer and changes it to another integer might do. It doesn't have to have anything much to do with what we call multiplication. We just define some operation that takes one point and turns it into another point, call it multiplication, and then see if it has desirable mathematical properties. And in this case, you use a really screwy operation, which goes like this. If you want to add 2 points, like P and Q, to get R, you put them on the curve and you draw a line and find the point of intersection. Then flip it, and that's what you call P plus Q. So it has nothing whatever to do with normal addition. And multiplication is just repeated addition. So you call that addition, and you call repeating that n times multiplying by n. And now you have something you can call multiplication and addition. It's just, remember, it doesn't really have to have any intuitive connection to any simple normal multiplication. You just have to be some way to take a bunch of integers and turn them into a different bunch of integers that can be repeated and reversed. So this is point addition and point doubling. So if you want to double the point, instead of drawing a line through the 2 points, you draw the tangent and take the intersection, which seems like a logical extension. And so this is the mathematical description of that. You have these 2 points, and down here all you do is this is the slope. The slope between 0.1 and 0.2 is y2 minus y1 over x2 minus x1. So you just take the slope, mod p.
I think the second one is d by dx.
What's that? Yeah, dy dx. Dy dx is the second one, exactly. Second one is, yeah.
You also, all those formula involve like another mathematical theory called Vieta theory to come up with all those equations.
Which one?
Vieta is called Vieta theory.
Vieta, I don't know. Yeah, okay.
It's a math theory.
Yeah, all right. Well, I know it from the differentials and stuff. So there's actually an animation of this. Let's take a look at that at 9A and see how it looks. From Cloudflare, in fact, because this is a lot of people want to understand elliptic curve cryptography. And these guys were motivated to make a little demonstration of it. So someplace down here, there we are. Supposed to, there we are. There you see it going. A plus B plus C plus A plus D, and so it goes. It's just a way to turn one point into another point.
I think he also has a little website that calculates all the numbers.
Yeah, that's right. Yeah, so anyway, all right. So there's the game of it, and you can do an example, although I find the example far from illuminating. Yeah.
So can the resultants ever be negative?
Apparently not, because you flip it around. Although to be fair, see, well, here's the point doubling. This one does go down here, so y is negative. X and y can in principle be negative. But I think x, and here x is negative. Yeah, I guess the values can be negative. We got a good point. Yeah.
When you do mod p, you also put another sign.
That's right. If you do mod p, that's right. Negative numbers are okay. Good point. All right. So one screwy thing about elliptic curves is you always have two numbers. And as we're going to see, when you're done, you just choose one of the numbers and use it as a key. Anyway, so this is what happens. The points on an elliptic curve, if you start at 5, 1, 2p gives you 6, 3, 3p gives you 10, 6, and on you go. And eventually, 19p gives you infinity. And that means it has order e equals 19. This remember, he did this before. You'd have a generator, and you repeat the operation. The generator produces some of the points in the set, not necessarily all of them. And that's the part of the set you can reach with that generator. Yeah.
So what is that? The theta that you call infinity on the x-axis, is that?
I think it. I don't think we can see it. They've got it here. Oh, I think it's off this. That's why they draw it here.
I think
It's
on
off the curve.
Yeah, I think it's on the x-axis.
Yeah, on the
All
x-axis,
the
it's
way
probably.
to the net far negative.
It sounds right, but I'm not sure. Yeah, all the way to the left. So that would mean if you somehow call it this point here, where you're going straight to the left.
We have an extreme factor in it. You get, that's where we have the minus.
Yeah. Yeah, and of course, yeah. Anyway, that's the game of it. So it can say how many points are on a curve. Remember this point, that only has 19 points. And so you have a theory. The number of points is bounded by a certain size here, but we don't really care. So this is kind of obvious. To make your curve attuned to 160 points, you need a prime at a length of about 160 bits. So you end up kind of like RSA, where the total number of points is close to the prime number you start from. So this is the elliptic curve discrete logarithm problem, which is just a small generation of the previous one. You're going to add the same point to itself d times, which is what you might call p to the d, and then get t, and you're trying to find d, knowing p and t. How many times you'll have to raise something to itself to get a desired point. That's the discrete logarithm, because we can do this addition, so we can take a known d and calculate t, but if we know t, we can't find d. That's the hard problem. So that's the game. If d is known, we are going to find an efficient method to handle large d's, but if d is not known, there's no good way to find it. Now remember, before we used square and multiply, because we had to do huge powers for Diffie-Hellman and RSA and El-Gamal. You had to take something to the d mod n. And so to take it to a high power, you did square and multiply. So here, you're trying to add it many times. So you do double and add is the equivalent of square and multiply. So here's the algorithm that does it. If you are, for example, trying to do some large thing like 2 to the 160 additions, which is what you're going to have to do, you don't try to do 2 to the 160 additions one by one. You double, double, double until you have p and 2p and 4p and 8p and 16p and 32p, and store them in memory, and then you add them up as needed to get the number you want. That's what all this does. So you take the you count down the bits, and you just keep adding. So you only do the log 2 of the number of additions. Yeah.
Does that give you an exact answer?
Yes, gives you an exact answer. That's also how you do it on computers. If you want to multiply integers by a large number, you don't multiply them, just shift them to the left. Shift it to the left doubles it, and left again doubles it, and left again doubles it. So you can quickly make a table of n and 2n and 4n and 8n and 16n.
How do you divide it?
It doesn't work for division.
With it?
Oh, and with this, it's the same issue. Backwards, it doesn't work. That's a hard problem.
But I mean, with binary logic, you must be able to divide.
Oh, you're probably right. But the problem is you can't combine them. To divide by a power of 2, you could shift it. But if you do have 1/2, 1/4, 1/8, and 1/16, there's no way to combine it to get 1/37. I think that's the problem. Anyway, so these are good questions. So here's an example. In step 1, you calculate p, then you double that, and you'll get, there we are. So here's the binary. So we're trying to get this value, 11010 base 2 p. And so instead of taking this number, which is something like 32, what, 1, 2, 4, 8, 16, yeah, something like 32, you just take the 0 means you ignore the first one. The second one, you have a 1 here, so you do the sum and add one of them.
No, you go reverse, go from both selected first, go the other way.
No, I think you have to go this way. But anyway, it's a double bit process. I mean, you double and add until you've got all those numbers, and then you combine them as needed. Anyway, I'm not inclined to struggle with your example here. I think at least it seemed clear to me the point is it's the logical equivalent of the square and multiply algorithm. So this means you don't have to try so hard to get them all. It just means the easy part of it can be made easy. That's all we care about. And the hard part of it cannot be made easy, the logarithm part. So let's see what you think of that. All right. And I do have a new homework with more math in it for those people that want the math. So Although I'm not planning to have homework where you manually do elliptic curves. That seems unnecessarily cruel. RSA is an appropriate complexity of homework where you really do it. And I've got some more homework about that. This elliptic curve stuff, I have no intention of making you code it in Python or anything. I'm not that interested. Although I think there are problems in the book where you figure out stuff like that about it if you really want it. But all right. So I guess I'll wait another 10 seconds. All right, we have a few Kahoot abstainers. 5 questions. So how long does your ECC key have to be? Yeah, or please, I think it was on the slide, but I don't remember Shane to say. 256 is the right answer. 256 is considered very strong. 130, I think, is the size that has never been cracked. 110 has been cracked, but 130 haven't been cracked. It was in a previous chapter. So 256 is very strong for ECC. All right. So what do you get with that equation? All right, that's a circle. That's a unit circle. Good. How about we're looking for an elliptic curve? All right, that's it. Y squared equals x cubed plus x. All right. What's the identity element? All right, it is infinity, which is a little bit mind-bending, but that's how it is. All right, which of these is not used in ECC? That's it, square and multiply is for RSA and Diffie-Hellman. All right, good. So I should make a note. W, NH, and Anna. I know who Anna is. Anna is actually the first name. NH, I think yeah, I remember him. Okay. So W is the only person I do not know.
Right here.
Oh, good. Okay, good. Good. Good, then I know who them all are. All right, so let's go back to the slides. All right, so let's talk about key exchange with elliptic curves now. So here's the game. You have a prime, an elliptic curve, and you have a starting point, P. So Alice chooses a private key and then calculates a public key by multiplying the private key times P. This is very much like Diffie-Hellman. And then they send that thing over the wire, the capital A. And Bob chooses a private key of little b and calculates big B by multiplying it and sends that over. Now each of them multiply what they've got by the thing they got over the wire, and now they have a key. It's very, very much the same as Diffie-Hellman. It's just that the operation is this crazy elliptic curve stuff in between. So now you have created a secret at both ends. Now you've created a secret with 2 sets of numbers. So how to turn that into a key for something like RSA or AES, I mean, something like AES, which is probably what you want to use, is not incredibly obvious. So what they typically do is just take one of them like X and then run it through a hash function to make it the right length. That's a way to turn it into a AES key. But that's the game. Now you have 2 people that can agree on a secret without sending the secret over the wire. And of course, the figuring out little a from big A is solving the discrete logarithm problem, and that's the hard problem. So they've got their own discrete logarithm problem for elliptic curves. Yeah?
Is that safe against quantum computing?
No. And we've been talking about that. No, none of these are going to survive quantum computing. The NSA, about a year and a half ago, announced an emergency statement that we had to abandon all our current public key systems and triple all the key sizes to get through the next 10 years. And the mathematicians I saw at the Cloudflare Summit said, that if quantum computers really work, then none of these algorithms will survive at all, not at any key size. They said, for example, RSA would have to go to 1 million bits key size, and that still wouldn't be enough. So the question is how good the quantum computers will be. But they're coming around really fast. IBM just made their 50-bit quantum computer, so 50 qubits. So it looks like the NSA is correct that quantum computers are really coming. And if they really make good ones, then all these schemes are going to be shot. And we'll have to have another category of public key cryptography, and no one knows what that's going to be, but in it, the NIST has already started the competition for quantum-resistant algorithms. But there are no approved ones yet. But that's, if you're a mathematician, that's a good field for research, is designing a quantum-resistant algorithm.
There was an
Yeah.
interesting announcement by the NSA maybe 1.5 years ago. I'm not sure if it was in the same one, but it was to not use ECC and just use RSA.
Yes. They said, well, they were recommending ECC for years at a short key size, like 160, because it'd be so efficient. Now they said, at first said, just go back to RSA, but they said you can continue to use ECC too if you triple the key size. So, I mean, the comparative security of ECC to RSA doesn't really change. That's right. At first, it seemed like they said just go back to RSA. That's currently the recommendation. But if you read the paper, I had charts. They also, and we'll see them, I think, coming by later. They say ECC is still okay for large key sizes. So I don't think ECC is any more vulnerable than RSA as far as anyone knows right now. But nobody really knows, not until we really have the quantum computers and see what they can do. Yeah.
So mathematically, one way you would modify this would be introducing a z-space, a z variable.
A z variable?
So a few slides back, you had the x squared plus y squared is equal to x cubed plus
Yeah. Yeah.
Would it mathematically make sense to add a z to?
Oh, no, a third dimension. No, it wouldn't do anything sensible. I mean, this whole elliptic curve thing is two-dimensional, and that's for a reason. If you had a third dimension, you'd have a whole other category of problems. And I'm not aware of any public key systems that rely on some three-dimensional function. There might be some, but none of them have progressed this far.
And,
Yeah.
and another thing is all these only work with simple y squared equal to x cubed. That formula, because there's a mathematical simple formula to calculate all the roots. So if you go up to another, like add another dimension to it, you screw up all the math, and you can get the algebra, to calculate the roots.
Yeah, yeah. I mean, it's a whole other issue there. And there may be some other hard problems on which you could base public key cryptography. These are the only ones that have gone far enough to be in use right now. But that's, yeah, it's exactly the point. Right now, we need new algorithms using a different kind of math to survive quantum computers, and that's currently the issue. And who knows what they're going to have to do. So once you have done the exchange of Alice and Bob, you now have a private key you've agreed on, TAB, and now you can just define a AES key, which you calculate from here. Here, they're just going to use X for the AES key. If it turns out to be an inconvenient length, which it almost always would, then you run it through a hash function to make it a fixed length. Like run it through SHA-1 and keep the first 128 bits or something like that. And now you can send your data with AES. So we can consider the security of this scheme. The parameters are significantly smaller because the attacks are weaker. This crazy addition process we've defined is harder to reverse than multiplication and exponentiation. So the best known attacks are the baby step, giant step, and Pollard row. You cannot use the number sieve, which they call something else here, number sieve, integer calculus is what they call it. That's the one that makes RSA get cracked very fast, but you can't use it for elliptic curves. So the number of steps required is approximately square root of p, where p is the size of the key. So that means if you have a prime, 130 bits has been cracked, but 160 bits has never been cracked. There's a series of challenges that people have been working on. And so if you have 160 bits, it'll take about 2 to the 80 steps to crack it, which is why nobody's done it, because that's too many calculations. And if you add 2 bits here, that doubles it. So 162 bits would be 2 to the 81, 164 bits would be 2 to the 82. So that's why 160 is safe, 256 is really safe, as far as anybody knows. Yeah.
So is the square of prime can be an integer?
What's that?
Can the square root of a prime be an integer?
No, but it's a square root of 2 to a prime, so it's an integer.
P is not a prime.
Yeah, P is a prime, but it's just P over 2. It's an approximation anyway.
Yes.
Okay, right.
But that's why you call it 160 bits. Yeah, that's right. Yeah, that's right. Yeah. All right. So like I say, if you had 256 bits, it'd take 128 steps to do it. So that's, now of course, the problem with quantum computers is a quantum computer can test something that takes 2 to 128 steps by only doing 2 to the 64 steps. The quantum computer gives you another square root. That's what they said at the Cloudflare Summit. It was very good way to see it. That's why the NSA said you're going to have to double or triple the key size to get reasonable security. But apparently it's even worse than that in the long run, because there's an algorithm that gets you faster and does not scale as fast with the number of steps, but this key size. So if you talk about how hard the calculations are to generate the key and perform this stuff, then there are 4 layers of computation. There's down here basic modular arithmetic, adding and subtracting, multiplying and dividing. Then there's this point multiplication stuff. Let's see, the group operation is the point doubling and point addition. Then there's point multiplication. And then at the top is the handling of the protocol for the key exchange. And it turns out that the most difficult operation is the one right at the bottom, this addition and subtraction. And multiplication of the fundamental points is the most difficult thing to do. So that's what you have to optimize if you want to make it work. And the here's the real results. On a 3 gigahertz CPU, it takes 2 milliseconds for point multiplication, or maybe 10 milliseconds on a smartphone, and on you go. So you can make dedicated chips for ECC, and then it can do a point multiplication in a few tens of microseconds, and you have to do, I think, something like 1,000 of those for a realistic case. So here's a simple thing. For RSA and Diffie and discrete logarithm, you have to add 20 to 30 bits to the key to double the attacker's effort. But here you only have to add 2 bits to the key to double the attacker's effort. This is why the NSA has been pushing it for a decade, because it would just save a lot of power and time and everything to just use ECC instead of RSA. But they reversed that 18 months ago. So there are a whole series of challenges of different sizes, just like there have been for RSA for decades, so everybody can try to crack them and win a prize when they crack them, to see in general how long the key needs to be experimentally. And 108 and 109 bits have been cracked, but nobody has cracked 131 bits. That's why somewhere around 130 is currently considered safe, and things that are longer, like 256, are considered not only safe, but to have a reasonable buffer for the future and for possible adversaries that have exotic powers like the NSA. So I say quantum computers would be the end for all these things. Now your book, which is several years old, was still saying quantum computers may never exist. I don't think everyone took quantum computers seriously until the NSA's announcement about a year ago, which basically admitted that they have one. So I think now quantum computers have moved from the realm of science fiction into we can see it coming. And so people are taking it very seriously. Yeah.
Is the NSA the only national entity or international entity that has commented on quantum computing and cryptography? Has like the FSB talked about it in Russia?
Well, this is an interesting question. As far as I know, America is the only country where a spy agency would ever talk about a thing like this. We're loudmouths over here. We have this freedom of speech and we have this freedom of disclosure and sunshine laws. So as far as I know, no one else ever would tell you. But I don't really know. But we do have the National Institute of Standards that does recommend things, and they recommend cryptography. And so they say what they're told to say by the NSA, which is often a lie to deceive us. So you have to sort of guess like what the real truth is behind what they're saying. So they didn't admit they had one, but they said it's really coming, you have to plan for it, which based on their previous statements seems to me to indicate that they have one. Because before this, they told us to quit using USB drives because we had figured out how to do Stuxnet. Every time they warn us about some technology issue, it turns out a few years later it's because we had developed the weapon that they're warning us about. And they didn't admit they had the weapon, but they gave us a warning that kind of gave you a pretty good clue. So this is one of the things Trump gets mad about. We telegraph our moves to our enemies. Yeah.
This is a bit of a tangent, but
Yeah.
do you have any comments on the shadow brokers? There was that big
Yeah.
article in the New York Times, and they're giving away the tools.
It's very, yes, absolutely. I mean, it's very interesting. I think it's extremely clear now. I mean, the shadow brokers and the NSA is in big trouble right now. They're leaking secrets. And leaking secrets ruins their entire business model. Their whole point is to have this exotic stuff that's 20 years ahead. They had analytical attacks against cryptography 20 years before the outside world had it. They probably got quantum computers 20 years ahead of us. And they're supposed to have it. They're supposed to keep it secret. And they're not doing any good at keeping the secrets lately, which has become much more difficult in this modern age of the internet and portable devices. But they're trying to figure out how to keep secrets. And the Russians are attacking us like crazy, not only with social media and direct hacks on our systems, but also by leaking out our NSA secrets. Since we don't keep them secret enough, the Russians are able to steal them, and they carefully leak them out to embarrass our government. So, I mean, we are currently under attack, and it's working very well.
Yeah.
What's that? The Shadow Brokers is a group. No one knows exactly who they are, but they publish every few months. They publish a magazine, and every magazine is full of political taunting of our government, followed by NSA secrets. There have been like 6 or 7 cycles of it. They keep dumping more NSA secrets. So they dumped out Eternal Blue and Eternal Romance in March of this year, which was used to make WannaCry. They keep dumping out, and before that, they dumped a bunch of router exploits. And they just keep dumping more stuff, and it's absolutely authentic NSA stuff. And so they are almost certainly the Russian military, but they don't admit that. They pretend to be somebody else, and of course you can't prove it, but they're almost certainly the Russian military, and they now claim that they've tracked at least some of it back to one guy with Kaspersky on his machine. He used the Kaspersky software to steal it, with or without the cooperation of Kaspersky. So that's why they said everyone had to quit using Kaspersky. And but that article from Nicole Perlman was very interesting because she points out they're very, very worried about the next leak. And there are a lot of people that think they have more leakers in the agency right now leaking the stuff out. Because he's got stuff that wasn't just from Snowden, it wasn't just from this one guy that got hacked. And they're trying to find the traitors in their midst, which is always the worst thing with any spy agencies when they suspect a mole that everybody is terrified.
I know, the article was saying too, it's affecting morale at the NSA. People are leaving for high-paying jobs, and
I've heard this.
They're outing some of their like special secret, like the TAO team people within the NSA.
I've heard this for years. That it is ever since Snowden. They say it is terrible to work at the NSA because they're having a huge witch hunt to try to find the moles. And once they suspect everybody, now suddenly everything is suspicious, right? How do you prove someone you're not a traitor? They'll find something about your personal habits or your way you spend money or something that looks suspicious. It's got to be miserable.
So is the government trying to figure out who's
Oh, yeah. Oh, yeah. They're now convinced there are moles leaking, and if not, there might be. And they're under huge pressure from the people on top saying, how do you know there's not another Snowden on your team? And how do you know that? They're making them take polygraphs every 3 months, and that's little more than a witch hunt there. It's madness. Yeah.
So the difference between like the cryptography attacks they might have and some of the documents is that these are actually in operations. So they could have been left on the box that someone had already found or someone captured it, sure that they sent over the network. It's much easier to lose these secrets than someone can.
Well, there are different ways you can lose different secrets. The previous theory, before they exposed this Kaspersky stuff, was that they got one of their staging servers, which is fairly common. But the Snowden docs he stole deliberately. But certainly the question, but apparently now they're saying somebody took the top secret stuff and put it on their home machine. And they could just as well have taken the promotional PowerPoints and put them on their home machine. And that's why they took, there was the Wen-Ho Lee guy at UC Berkeley, the nuclear lab there, that took well, I think it was complicated. I think he eventually got off, but his crime was he took top secret stuff and put it on the non-top secret machine where it could be stolen. That is a huge crime right there. And somebody did that at the NSA. And so, I mean, this is where they're probably going to like raid your home and examine your computers. I don't know how they're going to make sure you're not sneaking this stuff home. It's got to be bad for morale. And all along, they're paying very little. You can never tell anybody what you did. You can't get any glory. So the only thing I think that motivates you is a lot of patriotism. And when they're cruel and nasty enough to you, your patriotism may wane. You might say, I could be making a lot of money with a normal job. So, yeah.
Oh, no, go ahead, because I was
just in your opinion, if the NSA continues to erode, Snowden this, like what's going to happen? How's the world going to be different?
Well,
contractors.
Well, that's a very, people have been talking about this since the internet came out, that maybe we'll just have the end of privacy and the end of secrets, and everybody will realize you really can't hide anything anymore. People are arguing, like the military is getting fed up with passwords. saying we can't hide the passwords, you're going to use something else, but it's not clear what it's going to be. We could use biometrics. Apple's moved to it. Now people are claiming they can make a fake face and fool the Apple thing. And that's why the fundamental problem with that one is your face is everywhere. Pictures of you are everywhere. So your key is on public display for anyone to steal. It's very difficult to see what's going to come of it all. I think no one can predict it. But the internet basically is the source of all this, disrupting all of our previous ideas of secrecy and privacy in unpredictable ways. I remember 10 years ago, I was with the hippies that thought that maybe we should just relax and quit hiding anything and it'll be all right. But Bruce Schneier has an awfully good point. You really have to hide your password and your credit card number. You can't just let it all hang out in that regard. You might not have to hide your personal habits, but you do have to hide that stuff. And I don't know where we're headed. It's a very good question. I don't have an answer. Yeah.
So as far as international events, it's looking very bad because of what the Russian hackers might have done to change the election, not just here, but in other places. And
really, certainly, yeah.
How successful they might have been, like in this first attempt. Just think about just how serious these issues might be in the future, and how that could lead to wars, unrest, economic problems. I mean,
absolutely. I mean, the world is politically unstable. In addition, everyone's swinging to the right. You got the Nazis in Poland now. I mean, yeah.
In the book you're talking about, there was a cry that there was a plea or a request for encryption, standardized encryption by the NSA, which then, until then, had not admitted to existence. But they said there was a push from business. Didn't financial entities, in fact, have better crypto than the NSA back then?
Yes. I mean, the business sector wants crypto in order to do business. And I know when the American government in the previous system, they pushed out the Clipper chip and DES. The reason why they stopped was because European banks said they were going to refuse to do business with American banks if they were going to keep using DES, because it wasn't safe enough to match European privacy laws. And that, I think, is coming up again. Next year, the European privacy laws are going to force everyone to have the right to be forgotten. Because I've got students who say, there's something terrible about me on the internet, how do I get it off? And I say, you're pretty much screwed. But in Europe, you won't be screwed after next year. Everybody has to have some way to remove it. That's by law. So Google and Facebook and everybody has to have some way to do it. And maybe after it works in Europe, American privacy people will get that here. It's not technically impossible for stuff to get erased. It's just that they aren't required to bother, and they don't bother in America. Yeah.
But what's stopping someone from going to, say, the US Google page and then searching there? Or what's stopping someone from creating a page on the Tor network and serving that info about people that they want to erase?
You certainly have a very good point that you could not erase all copies of data. For example, people could just take photographs and put it in their drawer and then they've got it. Once something's on the internet, it's never can be made a secret again, but you certainly could get it so that it's not easy to find anymore. And that would satisfy most people, where when they apply for a job, their new employer is not going to be able to just do a Google search and find their embarrassing pictures anymore. They'll be removed from the main engines. And as far as the Europeans using American Google, we will see what happens next year, but I would think it's going to amount to the same thing as China and the Islamic countries, where they have to block that. They're going to have the Great Firewall of the UK stopping you from using American stuff. Or Google will have to, Google already does this. They already find your location and change what you see based on your location for things like sports, where you can only see it in certain locations. So the technology exists for that too, to release something only in one country and not in other countries. And I think the laws will force them to do that. So it'll be, and of course there will be ways around it. Like the Tor thing, hiding on Tor is certainly, you can't prevent that, but you can make it so it's difficult. And Tor is breaking the law anyway. So I mean, most of the stuff on Tor is breaking the law. Like most of it is illegal stuff. And so this will be another kind of illegal content on Tor, the forbidden searches. And so but I think in practice, nobody would bother unless you were a celebrity or something. So if they pass this law and they take reasonable measures, 99% of people will find that they can effectively remove the embarrassing stuff from the internet. And that would probably be a benefit for a lot of people, like people being stalked and stuff. It's a huge issue. Anyway, this is a very good question, very good discussion. Anyway, here's the NIST recommendations. It came out in 2016, recommendation for key management. So here's the game, comparable strength. Less than 80 is not safe enough at all. 112 is pretty good. That's like triple DES. and they say ECC is good with 224 bits, RSA with 2048, and down here is up to the level of AES 128. 3,000-bit keys is what they're now recommending for RSA, and that would be 256-bit keys for elliptic curves. And if you go up to AES 256, which is the strongest standard, which is considered good enough for top secret military data, then you see you need a 15,000-bit RSA key or a 512-bit ECC key. So it's not like ECC is no good, but the specific ECC they were recommending, because it was so fast, is not recommended anymore. They want you to use longer versions. And remember, we timed these, and it already took something like 30 seconds to make this RSA key pair. The RSA calculations become very burdensome as it gets longer. Yeah?
Is it just generating the key that flow, or do you also have to spend a lot of time on each single encryption?
Generating the key is the slowest operation by far. After that, encryption and decryption can be adjusted. You can make one fast and the other slow. And the normal thing you do is you choose a small e and a large d, so encrypting is slow, but decrypting is fast. That's the normal way you do it. And that's why one thing, next time we'll talk about signatures, RSA has one advantage. If you make it asymmetric like this, verifying a signature can be made very fast because you make creating a signature very slow. And that is, of course, the right thing to do because you sign something once and then people verify the signature thousands of times. Yeah?
With the prevalence of mobile devices, are these recommendations still the same? Is AES 256 on your iPhone still going to be best, or would it change for it?
I do not think it matters what device it's on. This is a mathematical statement of how hard it is to crack. The thing that changes, of course, on a mobile device is you have a weak processor and a weak battery, so you probably are willing to settle for a lower standard of security for performance. But it's certainly, I think, AES 256 on a mobile device is the same as AES 256 on anything else. Its mathematical level of security is the same. In practice, I know mobile devices are quite a lot less secure in what they do on Android. But I mean, there are a lot of other considerations. The main thing about mobile devices is you have limited processor and bandwidth, and the other thing about it is you're very likely to have the entire device stolen, which is a different threat model than most other devices. Yeah.
AES is very fast, even for AES 256. So
yes,
it's not really an issue, and basically
it's very fast.
Accelerated. So AES is super fast.
Oh, sorry, right. Certainly, you're right. Correct. AES is super fast on everything. So you're right. So it wouldn't matter. These other ones are ones that would matter. But you do need to do public key encryption on your mobile device too, to do something like a web browser.
Yes. So what actually matters though is how well the security of the phone protects your passcode from being brute forced, and
right.
how strong is your passcode. If you use a 6-digit passcode, maybe you need to switch to a passphrase so that it cannot easily be brute forced. But that's more important for security than using a stronger RSA.
Well, I would just say you have to find the weak link in security. For example, I found a lot of apps that use encryption that is so horrible that it's actually the bad link. Like there's a bunch of apps using the Caesar cipher and stuff like that. So it's just, you're right. If you used one of these, then something else would be the weak link. But you can be so stupid that your encryption becomes the weak link. Yeah.
A few pages back, didn't you say that
yeah.
the mobile devices were like half the processing power?
Oh, well, much less. And of course, battery life is a big issue too. That's a big issue. You don't want the battery to be draining too much, so it's a problem. Yeah. All right. So I think that's it. And I got a few more cahoots. This is a very good discussion. And all these issues come up from the cryptography. It leads to privacy and security and threat modeling and just all sorts of things. Now, cryptography can only solve so much. And then you've got a lot of other issues. But ultimately, it's the internet and Moore's law that disrupts our whole society because it keeps on changing so fast that nothing else can keep up with it. Not the laws, not the traditions. It creates future shock.
Blockchain is changing a lot of things. I just dreamed of a startup that's trying to put every human's identity on a blockchain. That's the business.
Yeah, that's.
But then there's no fraud, and there's pieces and all that taken care of.
Well, I'm sure I can think of a fraud. I could somehow go in and put 2 entries on the blockchain, pretending to be 2 different people, and that's not math. and now I can flip from one to the other. I could go steal your fingerprints and register as you on the blockchain, and then when you try to get on, they'll think you're me. I mean, this is what, when DNA came out, they thought it was perfect. And the very first DNA evidence case, they convicted the wrong man because the technician put the wrong label on the bottle. So he mixed up the two samples. So, I mean, there's always some part that can break. Even if some part is mathematically perfect, there are other mistakes to be made. Yeah, anyway, I'll wait another 5 seconds. All right. All right, so what's the best attack against ECC? All right, it's the Pollard row, good. These index calculus and number sieve are the same thing, but they only work against the exponential ones. And brute force is, of course, very slow, and there's almost nothing. This would be the perfect encryption if you have to really use brute force. Nobody has found one that good. Anyway. All right, how many steps will it take to crack 160-bit ECC? All right, the square root, 2 to the 80, that's right. All right, what's the most difficult part of the computation? Just the basic addition, adding and subtracting those goofy things, zipping around on that curve is the slowest operation. Archium has the highest answer streak. All right, so if you can crack 108-bit ECC in a day, how long will it take to crack 112-bit ECC? All right, that's it, 4 days. Every 2 bits doubles it, so you add 4 bits, you double it twice. Good? All right, so it's Archium and W. Good, I know who W is. And Ardugan, I know who that is. Good. Now I want to show you something about the projects. I've written a couple of new projects, and they're worth a bit of review because they're bringing up some issues that are not particularly covered in the book. At least one of them is. So let me point them out and say a few words about them. All right. All right, so I got a few straight up mathematics ones here. Here you go through the algorithm of find large primes, and here you start factoring large primes. So if you're interested in the math, the straight up math, this stuff is kind of fun. So here's Fermat's little theorem. If P is prime, A to the P minus 1 equals 1. If P is prime and A is not divisible by P. So if this condition is true, then it's probably prime. So anyway, this is all you have to do to find prime numbers, just a few lines of Python. You take a random integer, and then you check to see if the power equals 1, and if it's true, the test passed. And then you do it a few times, and I found you really only have to do it like 3 or 4 times to find a prime. Oh, I used the same old physics test I've used for years. When you don't really know how to do something perfectly, what you do is you try it 3 times for 3 rounds, and then you see if 10 rounds makes it any different. And if it doesn't, you call it the right answer. This is what physicists call a stable answer. When you have an approximate process that you can't improve, you say, well, doing more of it doesn't get any better, so we're going to stop and call this the solution. The reason why this thing fell into disfavor is because there are some numbers that will fool this test. But I didn't find any in practice, and I know people, in fact, use this to find prime numbers for a long time. So you can quickly find some prime numbers with this. So now you can test large numbers. Here's a 124-bit number. And you can find out if it's prime, because Python doesn't need any special libraries to handle huge numbers for simple things like multiplication and for modular. Taking it modulus something, so you can do the test a few times, and this one here, the test passed several times, so that's a prime. So on I go. 10 to the 300 is not prime. Find the next prime above it. It's really not very hard to do. And here's kind companion primes. Sometimes two numbers in a row are prime, like 11 and 13 are both prime. They're only two apart. That happens, and it happens fairly rarely, but it does happen. So find the first set of companion primes above 10 to the 100. And again, it's not very hard to do. So that's this one, just straight up math. Here's more of the same. This is factoring large numbers. Now that you can find primes, I used it to make some. Now if you have the product of two large random prime numbers, you can't factor it. That's the whole point of RSA and discrete logarithm, unless you make some kind of mistake. But in a CTF, this happened. This is pretty easy. So if I take a times a, 1001, it turns into this big number, and Python calculates the square of it correctly. However, it cannot calculate the square root correctly. If I take 10 to the 100 plus 1, that's 10 followed by 100 or maybe 99 zeros and then a 1. And then if I take a times a, it gets it correctly. It's 1 and there's a 2 here and there's a 1 at the end. This thing is 200 digits long. Now if I take b equals a times a and I import math and take the square root of it, I get the wrong answer. 10 to the 100 is not the right answer. The right answer is 10 to the 100 plus 1. So the square root function is not precise. It has some limit of places and it's less than 100. Typically, it's something like 10 or 20 for most programming languages. So there are various solutions for this. In a previous project, we used something like REPR function for this. I found a better one called decimal. This one is very nice. You import decimal. Now you can take decimal of an integer, and that one you can specify how many places you want. So I can set it to give me 200 places. And now, when I do decimal square root, I get the right answer, which is 10 to the 100 plus 1. So you can just adjust it to be as precise as you need. And it has no problem with 1,000 places or anything. It just moves right along. So this is how we can do large multiplication. So now, let's take this number. What are the factors of this number? Now, you can already tell from sort of the structure of this that it's 10 to the 20 or something plus a small number, plus 10 to 20 plus another small number. I took some numbers I generated with the previous project to do this. So, and here's the trick. This is the thing that's going to make this project work. I'm going to use numbers that are close to each other to make the primes, which of course is not what you're supposed to do. You're supposed to choose random primes. If you choose primes that are close to each other, then you're shot. Because then it's pretty easy to find them, because if they're close to each other, that means they must be close to the square root. Because you multiply two numbers to get to the top. One of them must be a little less than the square root, and the other must be a little bigger than the square root. So all you have to do is find the square root and then try other numbers near the square root. So here I give myself 50 places, and so the square root is 1 and a bunch of zeros and then 83 and change. So all I have to do is start at there and then try numbers -2, -4, -6 from there, because you don't need to try even numbers because they're not prime. So if I'm given the case that it's the number I'm giving you is the product of two prime numbers and the two prime numbers are close together, then you can find it this way. And all I have to do is calculate the big number modulus the small number. And when this modulus is 0, I found p as a factor. So I start from this p0, I go down by 2's, and you'll see here I hit a 0. So one of the numbers is 1 and a bunch of zeros and then 39. And I can find q by just dividing. So that's that one. Let me just turn off the gurgling. All right. So that's the game here. So here's a number to factor. I took one that's not so simple, factor that into primes. And then I get another one that's even longer, factor that one into primes. Because you can really do a lot in Python. 100,000 or a million things only takes a few seconds for simple calculations. So that's a little bit of factoring from straight up math you can play in Python with. And the other one I wanted to give you is something that really annoyed me when I did a CTF, which is that when you actually get RSA keys, they never come in this form we're using. They come in this irritating form like this. These are the things you get. And I never have really understood what is that garbage. So that's why I wrote this project, to go through it and learn how to use this garbage, because this is the thing called privacy enhanced mail format. It's been around for decades. And this is usually how you write down a private key and a public key. So you make it with OpenSSL. OpenSSL is the standard library on Linux for this. This is the one that brought us the Heartbleed attack. Everybody uses it. So when they make a mistake in OpenSSL, it rocked the whole world. But anyway, so this thing is called a PEM file. So if you just do OpenSSL gen RSA, it will get some entropy somewhere, I don't know where, and it will make an RSA pair, and the default is a 512-bit RSA because the original paper inventing RSA like 40 years ago used a 512-bit public key, which was considered secure at that time. Remember, this is back in the days of DES and stuff, when computers were a million or a billion times slower, and that seemed way big enough at that time. So that's the default. So this is a 512-bit. Then this blob of base 64 encoded stuff includes a whole bunch of things. And you can run it through ASN1 parse. This is called ASN1 notation. And that's what's defined here. This is from the RFC 3447 that defines all these standards. Straight up from there, this is the ASN1 syntax. It has a whole series of numbers. And as you can see, these are pretty familiar numbers. N is the large number. E is the encrypting number. D is the decrypting number. So D times E mod N is 1. I think it's mod P is 1. Then you have P and Q here. Then you have a couple of other numbers here, which we don't really need, but I guess they're helpful for some reason. All those things are in that blob. So when you just run it through ASN1 parse, it shows you all those numbers. And I highlighted some of them in red, the ones that are most useful for us. N is the product of P and Q. This is the E to encrypt, and that's the D to decrypt. And there are other things here. That's a version number. Remember, E is also always 65537 because it turns out that it can be a small number, and people almost always just use that value. And that's what this is in hexadecimal. So you can also display the public key. The public key is just P times Q. It's N and E, but the reason why you have the ability to make a special file with just the public key is that's the one you give other people. You don't want to give this one to other people, of course. This has P and Q in it. That's your private key. So you run the just pub out, and it will put out the public key, and the public key is just a blob of base 64. And you can run that through it turns out that running it through the same function to parse it doesn't turn it into anything useful. You have to use this other thing, this other syntax to do it, and then you get the modulus of 512 bits and the exponent of 65537 in a useful form. Because this is all for historical reasons. These things were developed decades ago for the particular case of mail, and you're using functions from that thing. So anyway, now you can make longer keys. Just put the link down here. Now you can make a key you might actually trust, like a 2048-bit key. And now the private key will be a lot longer, and the public key will be a lot longer, of course. So then the other thing I mentioned is you can encrypt the private key. That's what you're supposed to do, because if somebody steals that file off your disk, they get in there. So you encrypt it by just specifying an algorithm here. You can use triple DES or AES or various things. So here I encrypt it with AES 256. If you turn on an encryption algorithm, it will ask you for a passphrase. You have to type it in twice, and then your thing is encrypted. And now if you look at it, it will tell you it's still plain readable text, because all these things were intended to be sent by email, and email can only send ASCII text. That's why it's all base 64 encoded. And it always has this readable stuff. So now it is type 4 encrypted. So this is base 64 encrypted stuff. And you can only open it with the private key. So if you try to print out the public key from your private key file, you have to put in the password. And when you get the password right, then you get it. So that's the game. So now I give you some challenges. Here I give you a private key, and you got to find P. That's pretty easy. Then I give you a private key, and you got to find the public key, which is also quite easy. And that's as far as I made it required. Now I got challenges, which I thought you would have fun with if you're interested in a little bit of math. So now I give you a messed up private key. As you can see, I've covered a lot of it with X's. So portions of this are no longer extractable. And so find Q from here. You're going to find out that it's not that easy. And this one is even harder. That's why I made this one worth 20 points. Here I have 3 regions of redaction. The big X's along and another 3 X's in the middle. Up here, I have redacted out this portion of it, and repairing the missing pieces is a little bit of work. But anyway, you can now find Q in hex and get on a bunch of winners pages. So check it out if you're interested in a little bit of math and a little bit of programming. Yeah.
So how do they do the encryption for like Apple, the iMessage, which is supposed to be MMS and more safe than SMS?
I don't know exactly what they use. It's a good question. I would Apple's MMS. I don't know. It could be TLS. TLS is perfectly fine as far as I know, but maybe they have their own system.
And what happens if you go finally to the recipient who's got an Android? Does it decrypt it? Or?
That's a good question. I do not know. I don't know how iMessage works. I know the Tor people and the people that develop Signal write interesting articles about this stuff. And they go into great arguments about it. I don't know the answer. Yeah.
I'm not sure if I know the answer, but I remember reading a little bit about this sometime back. And it seems like every message that is sent to you, basically, Apple keeps a key for your device, your public key, and the device has the private key. So at the time that the message is sent, it is encrypted with all of the keys for your devices that it's supposed to be sent to. And then this special encrypted message is delivered to all of your devices. So I'm sure they also use SSL, like HTTPS, to basically transmit data back and forth. But I believe that the way that the messages are encrypted is your device, when you approve it for your Apple ID, will send some kind of a public key to Apple. That is then used by everyone else who sends you messages to encrypt everything that is sent to your iMessage.
Even if it goes to an Android, ultimately, what happens in the last leg?
Well, in that case, I don't know if there's any iMessage support for Android other than regular standard SMS. And if you fall back to cellular SMS, then of course you have no protection whatsoever.
Now, of course, I do know that Apple has a secure element, so they can store keys that cannot be stolen by any app.
Right.
And I presume that's what they're using for this, but I don't know. I know that's what they use for Apple Pay.
Yeah.
I don't know if they use it for this, but they could.
I mean,
Probably.
the hardware, the super.
It's in the hardware. Yeah, it's same as the TPM on a computer. They have a special cryptographic processor that holds keys and does the decryption, and the processor never sees the key.
It's a secure enclave, right?
Yeah,
And the vendor never sees your credit card number.
That's right. That's right. So they can put the key where it's really very hard to steal. No act of the processor can reveal the key.
Okay.
But I know they use it for Apple Pay, but I don't know if they use it for the messaging service, but they certainly could. And in Android, many Android devices do not have a secure enclave, so they are intrinsically less secure. But the more expensive ones do.
Oh.
Now, so the important part here is that your device encrypts the data that are being sent with the recipient's keys. But in order for this to work, you have to basically be able to trust Apple, and you have to be able to trust that you're connecting to Apple. So the reason that's important is someone could basically request Apple, like a law enforcement agency, to add their key and their device to your Apple ID, and then they will be able to receive every single thing that you receive,
Right.
or send.
And that's a huge issue. I know BlackBerry had to do this when they went to United Arab Emirates. They forced them to put a server in the country so they could see every message sent from the country in plain text. And Apple certainly is in the mood to not do that, but I don't know what they've done.
Yeah, so the system also means that Apple can't see the messages unless they, actually add their key to the ones that the messages are being sent to, because the key can only be decrypted by a device that is registered in this list of devices that receive this particular message. So unless they add themselves to the list, they can't see it. So your messages are protected from Apple, and they're should be protected in the past as long as whatever was sent to whatever devices in the past was only encrypted with those devices' keys. So unless the key gets compromised, the past messages should be secure. But in the future, the system doesn't prevent Apple or the FBI asking Apple to add another device to your Apple ID to basically capture the messages.
Like a wiretap. Yeah. All right, well, I'm going to stop the Zoom.
Which is much better than unencrypted email.
Covered things. And I know who everyone is, so I'm going to stop this recording. I'll go to the lab and we can continue. I'll help anybody who wants to work on projects. All right.